second section, more methods. So we just saw direct proofs only. They are the proofs that we saw. They are all direct proofs, but there can be different types of proofs. One very common way to prove something is proof by contradiction. So what is this? Let me explain this using a sentence. A proof by contradiction is a proof technique to prove a statement like this. To prove, so usually a statement looks like this. If P, then Q. So if you want to show this, proof by contradiction is going to be like this. By assuming P and also not Q, and finding a contradiction. So what is a contradiction? Contradiction is a statement that can never be true. Something like this. Like R and not R. So this is a constant contradiction. Not R and not R is always false. Whether R is true or false doesn't matter, it's always false. So we obtain something that is always false, contradiction. So if you assume P and also not Q, and if you find a contradiction, that means Q must be true, because not P, not Q cannot happen. Since assuming P, not Q cannot happen, in this case, we must have, or Q must be true. So this is conclusion. Q is true. So this is a typical flow of proof by contradiction. Assume the negation. You assume that the conclusion is false, and then you find a contradiction. Because of this, the conclusion must be true. That is the technique, proof called proof by contradiction. So notice that in proposition theory, I don't know. So proof by contradiction is nothing but this. Uses this fact. So we want to show, this is the thing that we want to show. P, if P, then Q. Instead of this, we prove equivalent statement. If P and not Q, then contradiction. You can show that these two statements, these two propositions are equivalent. You can draw a truth table, right? Then they are always have the same truth values. So proving this is equivalent to prove this. They are the same in terms of true or false. If you show this, you have shown this because they are equivalent. Is this okay? So proof by contradiction is very useful if you cannot prove this directly. If you can prove this directly, you don't need this, but if you are kind of stuck in finding a direct proof, you can try using this technique. So let me give you an example of this. So this is a very typical example of an indirect proof. You don't prove Q directly, but you prove in some kind of different way. for all n integer, if n squared is even, then n is even. Proof. Yeah, this is true. We can prove this. So now we assume this. This is the assumption. We assume n squared is true. In order to show that n is even, we suppose that this is not the case. So suppose that n is not even. That is equivalent to saying that n is odd, because n is an integer. If it's not even, it must be odd. So we assume that n is odd. We assume that this is not q. We assume that not q. And if you can conclude a contradiction, then this must be false, meaning n is even. So let's see what happens. Because n is odd, there is an integer k such that n equals 2k plus 1, right? Because we assume that n is odd. Now let's consider n squared. This is 2k plus 1 squared. So if you plug in then there, 4k squared plus 4k plus 1. Is this an even integer or odd integer? It's odd because it's 2 times 2k squared plus 2k plus 1. 2 times integer plus 1. So it's odd. So what is this? We assume that n is even, but now we are saying that n is odd. This is contradiction. Usually we say the contradiction to the assumption. Assumption that n squared is even. You cannot have both. N squared even, n squared odd. This means we made a wrong assumption. That was this. This is wrong. So n must be even. So this is then end of the proof. This is a typical example of proof by contradiction. Is there any question? Is this clear? Do you think this makes sense or not? Confused? Yeah, actually this is very simple argument in this sense. Suppose that we have 2 possibilities like this, A and B. Suppose that you know that the answer is A or B. And suppose you also know that A is not the answer. Then what can you say? B is the answer. It is something like that. We have either A or not A, but we just cross this out. Not A cannot happen. Then that must be A. A must be true. This is just the same argument like that. This cannot happen, so this is true. It's simple like that. Okay, let me give you one more example just for clarification. For all real numbers x, y, this means the set of real numbers, if x plus y greater than or equal to 2, then x1 greater than or equal to 1 or y is greater than or equal to 1. Yeah, this kind of thing can be proved directly, I think, but indirect proof by contradiction is very useful for this kind of statement. So we have a statement like P, if P then Q. So let's prove this. So what is the first sentence then here? Suppose that the conclusion is false, right? we assume that the conclusion is false. Try to find a contradiction. So suppose that the conclusion is false. In other words, what is the negation of this then? X is greater than or equal to 1 or y is greater than or equal to 1. What is the negation of this? X is less than 1, and here? And y is less than 1. So we assume this. And we want to find the contradiction. So, can you see the contradiction? Let's add two numbers together. We have two real numbers, both less than 1. If you add 2, it must be less than 1 plus 1, which is 2. Did you find the contradiction? Yeah, this is contradiction to the assumption. So this and this cannot happen together. If this is R, this is not R. So that means our assumption is false. So this cannot happen. Therefore, what? This is not the case, so x must be greater than or equal to 1, or y must be greater than or equal to 1. All right? Can you do this? Do you think you can prove things like this? All right, good. Yeah, I'm going to show you an interesting example. All right. If 1 equals 2, then, how can I say? Every triangle is a square. Is this true or not? Is this statement true or not? True? If it's true, can you prove it? Okay, let me show. Let's prove this. Let's try to prove this. Can you imagine a proof? I'm going to use proof by contradiction. Okay? Suppose that the conclusion is false. Suppose that the conclusion is false. Okay, you don't have to state, I'm not going to state the negation of this. But if you want, what is the negation of this? There is a triangle which is not a square. Quite reasonable, but yeah, you don't need to state it. By assumption, 1 equals 2, right? Because of this. It's a contradiction. Because 1 is not equal to 2, right? We have obtained a contradiction. That means this was false. Thus, conclusion is true. This is true. Can you believe it? This is a valid proof. Do you see? Do you see that this is a valid proof? Yeah, it just follows our there's nothing wrong in this proof. This is a correct proof of this statement. And actually, we didn't really use what this is. It doesn't matter what this statement is. This is because in every conditional proposition, if the assumption is false, it is always true, right? And that can be proved in this way, if you want. Yeah, this is not very usual proof of something, but I just want to show you that we can prove kind of formally anything like this. Does this make sense to you? So proof by contradiction is like this. Yeah, I'm going to show you one more example, which is quite famous. Square root of 2 is irrational. This is a very well-known theorem. Proof. Yeah, I think it's very difficult to prove this directly, I think. But indirectly, we can prove this not very difficult way. So what does this mean? Irrational. What is the definition of an irrational number? What is the definition of a rational number? Do you remember the definition of a rational number? 유리수. This means 무리수 if you want. What's the definition of a rational number? Yeah, so it's a real number that can be written as a quotient of two integers, right? So suppose that this is not the case. Suppose not. So for simple people, simply say that. Suppose not. That means, yeah, suppose that in full sentence should be like this. Suppose that square root of 2 is not irrational. But because, it takes time to write this all the time, just say, suppose not. Suppose the conclusion is not true. And if you can find the contradiction, then this will be proved. So then what is that? We know this is a real number. We should assume that. A real number that is not irrational number, then square root of 2 is rational. Rational. Because we assume that it's not irrational. Question? Oh. Yeah, we will assume that square root of 2 is a real number. Yeah, that's a good point, but we will assume this. We assume this. Yeah. Yeah, actually, real number is not a very easy number to understand. Actually, in order to define real numbers precisely, you have to take analysis course. It's a math major, maybe second year course. And in that class, we will define real numbers precisely. But in that definition, you can show that square root of 2 is a real number. But for now, because we haven't really defined what real numbers are, the precise definition of a real number is quite complicated. So we will assume that square root of 2 is a real number. All right? Not satisfied? If you are not satisfied, take analysis course. We are not going to do this here. So square root of 2 is a real number. So it's not we assume that it's not a irrational number. So it is a rational number. That means there exists, I'm going to use the shorthand, a comma b, real integers, such that what? Square root of 2 equals a over b. This is the definition of a rational number, right? Now, okay, we can assume that GCD of a comma b equals 1. They don't have any common factors. Why can we assume this? So for instance, we can assume that it's not something like 18 over 9. We can assume that A and B are not of this form. They don't have any common factor. Why? If they have common factors, we can divide out these common factors. So for instance, okay, if they did have common factors, we can divide them. Okay, so if you want, we can assume this by dividing A and B by their GCD, greatest common divisor, if necessary. Okay? This is okay? So basically you have a rational number, so you have a fraction. But they may have something, because you don't know what fraction they are, so maybe it can be something like 6 and 84. But in this case, you divide both numerator, denominator by their greatest common divisor. So you divide this by 2, like 6, 3, 4, 2, until you don't have anything in common. So maybe divide by 3, 21, 1, 4. So now they still have, wow, amazing, 2, 3. So now they don't have anything in common. In this way, you can always reduce this to A over B, where A and B don't have anything in common. Is this fine? Okay. Now we will do the following. Now B square root of 2 equals A, if you multiply B both sides. Now take the square of this. If you do this, you get 2 times B, B squared equals A squared. All right? Now A squared is an even integer. So A squared is even. But we showed that if A squared is even, then A must be even. So A is 2k for some integer, k, right? For some k. Now substitute 2k here. Then 2b squared equals 2k squared, which is 4k squared. Now divide both sides by 2, then we get b squared equals 2k squared. So b squared is an even integer. That means b is an even integer. So b must be written in this way. L is for some L. Right? Now what? Then A and B have common factor 2. So GCD is not, that means GCD of A and B is not equal to 1. Is that right? So we had this GCD equal to 1, GCD not equal to 1, contradiction. That means the first assumption here is wrong. That means square root of 2 is irrational. So this is the end of the proof. So we assume that the conclusion is false and we found the contradiction. That's the proof. So we have seen proof by contradiction. Now there is another type of proof. Proof by cases. Probably the most simple-minded proof. You consider all possible cases and then prove each case separately. So this technique divides assumption. So we have assumption, if P then Q. Assumption into several cases and prove each case separately. So you just list all possibilities when the assumption occurs and you attack each case separately. So maybe sometimes this takes some time, but it can be useful because I think usually people call this like 노가다 proof if you want. Because you really did everything, you list everything. Yeah. You will see what I mean by this. 2m squared plus, but still it's a valid proof. No solutions in positive integers. Positive integers. So in other words, for every positive integer n and m, this cannot happen. This cannot be true. So let's prove this. Obviously, you cannot check all all positive integers because there are infinitely many. But because of this, we can restrict the possibilities of n, m, and n. So since 2m squared, obviously 2m squared is less than or equal to this, because this is always non-negative. If you take the square of something, real number, it's always non-negative. But we know that this is 40, right? So if here m squared less than or equal to 20, what is the possibility for m? That m, a positive integer, we are restricting to positive integers, m is equal to 1 or 2 or 3 or 4. It cannot be bigger than 4, because if it's 5, it will be bigger than 20. Similarly, 3n squared less than or equal to 2m squared plus 3n squared equals 40. So here, if you divide both by 3n squared less than or equal to 13 point something, we don't care. So n is either 1, 2, 3. 3 is the maximum possibility for this. So there are 4 possibilities for m, 3 possibilities for n. So n comma n is either one of these. How many pairs are there? 4 times 3. So there are only 12, right? 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3, 4 comma 1, 4 comma 2, 4 comma 3. You check all of these pairs and show that this is not the case. Obviously, we can do this. You check is. Okay, 2 times 1 squared plus 3 times 1 squared equals 5 is not equal to 40. So this is not a solution to this. And you do the same thing for this and this. You do this for 12 times. And none of them satisfies this. So after doing this, you will end up this conclusion. So no solution. But of course, I omitted this part, but that can be checked. You have to, in this proof, we have to list all of these 12 things. But I'm just omitting that because it's trivial. So this kind of proof is called proof by cases. All right? So may look a little, not very clever, but still it's a proof. All right. Another thing, proofs of equivalence. Equivalence. So statement is not always of this form, if P then Q. Sometimes we have a statement like P is equivalent to Q. So P if and only if, or if and only if. We know that this is equivalent to if P then Q, and if Q then P. We know that they are the same, equivalent. So if you want to show this, you can instead prove this and this together. So example, very simple statement. For all integer n is odd if and only if I write 2 f's like this, then it means if and only if n minus 1 is even. Pretty obvious, but let's prove this. This is a proposition of this form, P if and only if Q. So we need to show 2 things. If P, then Q. So usually we write this. This means, this symbol means we are going to show this thing. If P, if this is true, then this is true. Okay? This is what I mean by this symbol. So we assume that n is odd. We want to conclude that n minus 1 is even. So because n is odd, n is what? 2k plus 1, right? For some k. For some k. Then what is n minus 1? 2k. So it's even. That's it. The other way. Now we assume that n minus 1 is even. Because of that assumption, n minus 1 can be written as 2k plus 1 for some k. Then n is what? Oh, no. This is a contradiction. 2k plus 1. So n is odd. This is it. This is the end of the proof. We just proved two things. So this is an example of a proof of equivalence. But sometimes we have not only two, but more than two, like 3 or 4. Sometimes we want to show equivalence of many, many statements. So in order to show that, the equivalence, several statements, several propositions, say P1, P2, Pn. In the previous example case, we had just 2. But suppose you have n. Yeah, you can prove this if you can show that any 2 of these are equivalent. But there are too many cases like that because there are n choose 2 or n times n minus 1 over 2. There are too many. But we can prove this. We prove only this. If P1, then P2. And if P2, then P3. And dot, dot, dot. If Pn minus 1, then Pn. And finally, if P1n, then P1. So you only need to prove n plus 1 statement, because this will imply that they are all equivalent. Do you see? Why? Because this means if this is true, then this is also true. If this is true, this is also true. If this is true, this is true. And finally, if this is true, the first one is also true. They are all in circular order. So if one is true, if you follow this arrow, you can reach any proposition. So they are all equivalent. If you show that these n plus 1 statements separately. Okay? So for example, so A, B are set. Prove that usually in math textbook it looks like it states like this. The following is a very common phrase. The following are equivalent. So 1, A subset of B, 2, A intersect B equals A, 3, A union B equals B. So what this means is that these 3 statements are all equivalent. This is equivalent to this is equivalent to this, and this is equivalent to this. So any 2 pairs of propositions, they are equivalent. But you don't have to show any pair. You all need to show just n plus 1 things. But in this case, they are the same. But anyway. So proof. You need to show this. This thing, and 3, then 1. This thing. You need to show just 3 things. Instead of showing, if you don't use this, if you want to show the equivalence of every 2 pair, every pair of 2 statements, you have to show 6, right? Because if you want to show the equivalence of 1 and 2, you have to show if 1 you have to show these two things, right? And for this pair, you have to show this thing, right? And for this pair, you have to show this. So you have to show 6 things. But these 3 are enough, because this will imply all of this, right? Yeah, it's a quite good deal. You just reduce the statement into 3 things, essentially. So how can we show this? I think now we can show this. So exercise. Prove this, I think. Any question about this? Now, let me talk about existence proofs. So, proposition, the theorems that we saw look like so far like for all x, if p then q. But we can have a statement like this: there exists x, p of x. We can have a statement like this. And this can be proved by finding an example of x such that p of x is true. Just one example is enough, because this is what it says, what it's all about. One example. Doesn't say that there are many, at least one. There can be many, doesn't care. This statement only cares about just one. One is quite enough. So example, for all real numbers a and b, if a is less than b, then there exists integer, real number, such that x is between a and b. What does this mean? When you have 2 real numbers, distinct real numbers, there must be a real number which lies between these 2 numbers. Can you prove this? Yeah, you know, if you think about this, quite obvious. So a and b in this real line looks like this. Is there a real number between a and b? Yeah, there are plenty of them. You can just select one of them. Let's pick the middle, that thing in the middle. So if x equals a plus b, the average of this, then what happens? Yeah, is it? Because if you want to really find a very precise, if you want to be very precise, what is x minus a? It's going to be p minus a over 2, right? Which is, because b is bigger than 0. And b minus x is again b minus a over 2, which is also bigger than 0. So we have this. Oh, we have found just one example. That is enough to show this, because the statement is just the existence of one real number. So such a proof is called a constructive proof, because we explicitly constructed an example. So if a and b are given, x is this. We just showed you very clearly that what x is, right? Constructive. There is a proof, non-constructive proof also. We will see this in the next page. Very, very clear. Just explicitly show the formula for x. This is an example of a non-constructive proof. Suppose that, okay, let A be the average of n real numbers. So SIs are real numbers. They are all real numbers. Okay? Then prove that there exists I such that SI is greater than or equal to A. So what is the meaning of this? So you have average, you have n numbers, real numbers, and you know the average is A. If the average is A, one of these numbers must be at least as big as that average. How can you show this? We can prove this using the technique, proof by contradiction. So suppose that as we assume that the state conclusion is false. In other words, SI is less than or equal to A for all I, 1, 2, n, right? This is the negation of this conclusion, right? There exists I such that this. If this is not the case, that means every SI is less than, strictly less than A. And if you can find a conclusion, contradiction, then we can show that this is indeed the case, right? Now what happens? So S1 is less than A, S2 is less than A, Sn less than A. So let's add all of these inequalities. And S1 plus ... Sn is less than A plus A plus A, which is n times A. Now divide both sides of this inequality by n, then we get S1 plus ... Sn over n less than A. It's a contradiction. It's contradiction. To what? Contradiction to what? To the assumption. This is the assumption. We assume that A is this. So there is I such that Si A. This is the end of the proof. Because we assume the false statement, that must be the conclusion must be true. So here, did I explicitly exhibit Si? Did I say that in this case S1 satisfies this? No, I didn't say that. I didn't say that S2 satisfies this. I didn't specify what I should be. So this is an example of a non-constructive proof. So this is a non-constructive proof because I didn't construct the counterexample or I satisfying this. Non-constructive proof. Sometimes the proof is like this. Doesn't show you what this is, but it just tells you that there must be something. We don't know what that is, but there is something. Still a proof. Do you like a proof like this? Which proof do you prefer? Constructive or non-constructive? Yeah. Some proof is better than the other is a personal preference. No one can say this is better than that for sure. Some people like constructive, some people like non-constructive. But I think more people like constructive proofs because we can really see what those are. Because sometimes we not just want to see the existence of something, but sometimes we really want to see what those are. So constructive is, in that sense, are better